Continuing in Chapter 3, we're now going into Topic 2, Logarithmic Functions. The objectives: change from logarithmic to exponential form, change from exponential to logarithmic form, evaluate logarithms, use basic logarithmic properties, graph logarithmic functions, find the domain of logarithmic functions, use common logs, and use natural logs. Now I'm going through the objectives because I know some of these terms may be a little foreign, so repetition would be in order. All right, the definition of a logarithmic function. And what I'd like to do is set this up for you. All right, we'll pause, go to the whiteboard. I'd like you to copy some stuff down. Again, there was material that we will review shortly, but here is what we see up there. Y equals b to the x power. This is in its exponential form. And then log by of y to the x power here. This is the exponent. So looking at it, I've switched them around a little bit here, that if we have a base to an exponent, which is what we're illustrating in these little boxes here, this equals the answer. Y is the answer when you raise this base to this exponent. Now in the log form, we have the base, that's still the b there, but the y, remember, is the answer. So log base of an answer is equal to an exponent. So again, these little sketches, when we are converting from exponential power to logarithmic, and something to keep in mind. All right, let's go back to our regular board. I'll leave that there. And a couple of things we need to know as qualifiers: that x needs to be greater than 0 and b is greater than 0 and b, that is the base, cannot equal 1. Because remember, 1 to any power is still 1. All right. So here they're giving us this expression, and hopefully you have some good notes on this. Now, for example 1, we're asked to convert each in its from log to its exponential form. And let's go to our little boxes again. You have this on the other page, but I wanted to put it here again so we can use it. So here it is in its log form. So our base is 7. Our exponent is 3. And our answer is x. They've just written it this way and another way to write it. All right, here our base is b. Our exponent is 2. And our answer now is 25. Now, keep in mind, you can almost figure out what b is going to be here. What do you think b is? Well, what squared is 25? They're not asking for that, but they will later. B is a 5. And then for this one, our base is 4. Our exponent is y. And our answer is 26. So again, practice. And keep referencing our values above here. This is example 2. So we want to put this in its log form. Well, we use the word log. Now, what is our base? So my technical advisor spotted a little error here, so let's check that out. So again, we're going from exponential form into log form. So what's our base here? Our base is 2. Our answer is x. And our exponent is 5. Okay, that's better. All right, for this next one, we have our log. Our base is b. Our answer is 27. And our exponent is 3. Now, later, we're going to have to find out what some of these letters are. We'll pass this up for now. Now, this one will be log. Our base is Euler's E. Our answer is 33. And our exponent is y. Okay, again, following this protocol, switching back and forth should be relatively easy. Logarithms, example 3. And we're going to start with estimate or evaluate this. Well, if we put it in its logarithmic form, from its log form, our base is 10. We don't know the exponent because that's not out there. Think of that as an x there. But we know our answer is 100. So 10 to what power is 100? Well, 10 to the second power. So that's what would go there. Now let's evaluate this one. Here our base is 5. Our answer is going to be 1 over 1/25. So what exponent brings 5 to this fraction? Well, we know it has to be negative. And 5 to what power is 125? Well, 5 to the third power here. So 5 to the negative 3 then is the answer. And they go through it here as well. And in example 4, evaluate this. Well, again, our base is 36. Our answer is 6. So this exponent here has to be to some fraction, something over something. And what did we say the fraction 1/2 was equivalent to? Well, that was taking the square root of something. So in this case, the square root of 36 would be 6. So our fraction here is 1/2. And they've worked it out for us here as well. Now in example 5, we have the log, base 3. Now what I'm going to do is convert this to its fractional exponential form. Now what is this equivalent to? Well, we said we could remove the radical sign. That'll give us our base, which is 3, our radicand. Now, the index number becomes the denominator of our fractional exponent. And the 3 has a little 1 there that we don't usually write, but that makes it this. So this value then becomes 3 to the 1/7, which is what they're showing you here. So in converting this would be log base 3, and the answer up here can now be listed as 3 to the 1/7 power. So our value then of this, the exponent, is the 1/7. Now we had mentioned that this configuration log base 3 of 3 is actually a 1. And then whatever exponent is up here, that is what the answer will be over there. So our exponent is 1/7. So this answer becomes 1/7, converting this from its radical form to its exponential form. Now, this is going over what we just mentioned, but perhaps a little clearer here. It says here, if we have log base b of b, this equals 1. Now, what is our exponent of this b here? It's a 1. So this part is 1. 1 to the first is 1. So this is what they're showing. And anything to the 0 power is 1 as well, from a very, very early lesson on that. Number 6 now, example 6 is an example of this. So we have log base 9 of 9. What does that equal? Well, if we convert it to its exponential form, our base is 9. Our answer is 9. So what exponent gives us that? Well, a 1. Well, there's a 1 there. So what is the value of this in terms of its exponent? It's a 1. So they're showing us that again. Now, as we look at example 6, the second part here, we have log base 8. The answer is 1. So I'm putting it in its exponential form. There's 8, our base. Our answer is 1. Now, what would the exponent be for something that will give us a 1? Well, anything to the 0 power is 1, which we've mentioned before. Anything to the 0 power is 1. So there is our answer, that this would equal 0. That is the exponent in this form, where our base is 8 of 1. The answer, the exponent, is 0. So again, reviewing the rules, and again, nice about these videos, if you ever need to review them, you can pause, of course, go back and watch it again. Now, looking at this, the inverse property of logarithms, we can see here that this portion is a 1, so that x equals x. We reviewed this a couple of times. And then this is if we have base to a logarithm b of x, this x equals this x. This is the inverse property of logarithms. Now let's go on to some examples. So evaluate. This is example 7. And nice to have an easy one. So here, log base 7 of 7, 8. Well, this 8 will equal 8, as they show here. And 3, exponential form, log base 3 of 17 will just equal the 17, as we see there. So hopefully something easy. Now, we're going to go into some background. We're calling this example 8. I'm going to show you these two slides, And I'm going to what I think will be an easier explanation of all of this. So I'll set the page up and we'll go to the whiteboard. Now I'm copying some stuff, and what I'd like you to do at this time, pause, and we're going to have you fill these in shortly, but right now just sketch what I have here. Now the first thing I'm going to do is convert this f of x, the function symbol, that we said we could put a y there. Y can always replace a function symbol. Now here, you'll notice we have y equals 3 to the x power. The inverse of this, or when we say something is an inverse, we exchange the letters y and x. So you see that here. The y is now an x, the x is now a y. The inverse of the exponential function is the logarithmic function. Okay, so what we're going to do now is fill these in. So if x here is 0, 3 to the 0 power, anything to the 0 power is 1. 3 to the first is 3, 3 to the second is 9. Now, when it's 3 to the negative 1, it's the reciprocal of what's here for 3 to the first. So this is 1/3, and this will be 1/9. Now here we have the y values. We want to find out the x values. So if y is 0, 3 to the 0 power is 1. This is 3. This is 9. And now these will be the reciprocal, 1/3 and 1/9. Now, the nice thing about the slide is they're going to graph this for us, and they've done a really nice job. So I'll just go back to the screen and then go to the graph of this. And there it is. So they've plotted all the points. Now the red line, the red curve, is the exponential growth. The blue curve is the logarithmic growth, and it's the inverse of each other. Now, some other words I want you to put there. For instance, if you draw a line right through the origin, and whose equation is y equals x. So over 1, up 1, over 1, up 1, over 1, up 1 from an earlier lesson. This is called the axis of symmetry. And all these words are for your notes. Now, as the red curve gets closer and closer to the x-axis, it never reaches it. The fractions get smaller and smaller. So we call a line that something gets close to but never reaches an asymptote. Some vocabulary words here. And since our x-axis is a horizontal axis, we say for exponential growth, our horizontal asymptote is the x-axis. Now the equation of the x-axis, interestingly, is y equals 0. That would be a horizontal line going through the 0 value for x. Now the blue line, as it gets closer and closer to the y-axis, never reaches the y-axis and is the vertical asymptote. Okay. And we've already defined that. This is an E here. Now, what's the domain and range of each of these? Well, the domain of our exponential function, this line eventually goes off to negative infinity in that direction and over to the right in positive infinity. The range now are the y values. It's going to start, never reaches 0, so parentheses to indicate it never reaches 0, and then to positive infinity. The domain for our logarithmic growth, again, the blue line approaches the x value of 0, but never reaches it. So this is parentheses 0 to positive infinity, and then goes off to the range as it continues to go up eventually to from negative infinity to positive infinity. Notice the domain and range are just the opposite of each other as we see it here. Now the next slide, and again pause to be sure you all have this in your notes. As we go to the next slide, it's going to give us a lot of what we've just covered. Hopefully I simplified it a little bit here for you. You can pause and read this if you like, and then going on to the domain, which we've done. And now finding the domain of a logarithmic function. Now we're calling this example 9. So find the domain of this function in its log form. Well, remember, this value here can never be a negative value when it ends. So that if we equate what's in parentheses, that this has to be greater or equal to 0, which is what they're doing here. We find that the answer to this is x is greater than 5. So when we think of the domain, it's going to be a parenthesis. 5 is not included. 5 will be your vertical asymptote, so to speak, and then it goes to positive infinity. And if you put this into your graphing calculator, you see you get a curve that looks like this. Now this vertical green line going through 5 is your vertical asymptote. Again, a vertical line, the equation here is x equals 5. And we write the domain in this fashion. All right, we're winding up. We're almost finished. Now here we see the common log. And remember we said the common log, the base is 10. And we don't usually write the 10. If you just see it log, the assumed common log is base 10. Let's go on to an example now. Here the percentage of adult height maintained by a boy who is X years old can be modeled by this logarithmic function, where X represents the boy's age from 5 to 15, and the other represents percentage of his adult height. Approximately what percent of his adult height has the boy attained by age 10? So we have the 29, we have this. We're just going to substitute for the x here 10. So this becomes 11. Now you can just put this into the calculator. 29 plus 48.8 log 11, and the answer should come out to 80 decimal 0.8, but converting it to percent would be 80%. Okay, when I put it in the calculator, I see it's giving it as a percent, not as a decimal. There is this decimal part. We are to round to the whole number, and there's where we get the approximate 80%. So again, you need to be trying these to be sure you know how to use your instrument. Now, here are the general properties of common logarithmics functions here summarized. We've gone through all of these. These were the inverse properties that we've mentioned. Again, check them out. Tape is running long. We don't want to have this too long. We're almost finished. Now, natural logs. The natural logs are indicated on your calculator by ln, and it's from the Latin logrimus naturalis. In English, natural logs, Latin, but this is the symbol on your keypad here. Now again, the base of natural logs is e that we don't write, just as we don't write common logs 10, but keep in mind it is there. Some summation of this. All right, we're almost finished now. And then the natural log properties are pretty much the same, except instead of the base 10, we're using base E. All of the same properties apply. So here is our last application. Here they're showing us the difference in air temperature from 72 to 96, where there's a difference of 49 degrees in the first hour. So based on that, what would the nearest degree after 30 minutes? So X is after 30 minutes. So where the X is, we put the 30 minutes. So put this function into your calculator and see if you get 34. Now, when I did it properly, I ended up with this that I round off to the nearest whole degree, which is 34. Now, as I first put it into my calculator, I forgot to close the parenthesis because when you do this, I put it in, I had a single parenthesis there, and I didn't put a parenthesis there. And as a result, I got a different answer. So again, you have to put these in correctly, and that will be our lesson on topic 2 of chapter 3.